Alrighty, so I think we can start. So I hope you guys didn't go splat on the ice this morning. That was pretty bad. / interesting. Anyway, good day for studded ties, right? Yeah. Okay, so we're going to talk more about this branching network stuff, and I guess I want to emphasize that it's a big deal, right? I mean, this is the dominant sort of structure on the Earth if you look at it from space, the actual geomorphological structure that is. And it matters tremendously. Rivers are a big deal for us. And then, of course, the branching networks inside us are pretty important things. Keeps us sort of running around, so we need to know about those things. So I guess I'll call them supply networks, but it's optimal supply networks, right? That'll be a sort of a next section. So we're going to sort of describe these things and then eventually start to talk about, how efficient are they, how well put together are the networks we see around us. Okay, so I did a few little drawings because I want to explain some basics about how you might go about deriving, from a satellite image, how that gets. I'm just going to talk about how this works, how that gets transformed into basically a matrix, and then you have to figure out how to extract the networks from that, right? So there are some harder things too. If you have, say, a picture of maybe the tidal areas, right? That's a bit harder because things get wider and so on. So you want to, you need to use some image recognition techniques to kind of map out the shapes because you're really worried about the width of the rivers and so on. That's also true of some of the imaging for blood networks, right? So that's just a hard thing to do well because you're going to end up with this 3D, right? Reconstruction of a network, and then you have to sort of think about how you're going to go in there and we talked about stream ordering, so I will go through that a little bit again, but how do you do that for those networks? And I mean this in a computational way, right? So the way that's been done, that's the data I've presented to you has been by people actually getting the goop out on a table and counting things, right? So that's laborious, right? But we want to get imaging of 1 million people and here are all these networks inside them, and so let's do it fast. That's how you transform sciences. Okay, so I'm going to talk about that a little bit. I have just a couple of things. So I did have some hiccups with the assignments, so I'm sorry about that. It took a while to get them to link to have the assignments online, but they're here, and they're due a week from Friday, right? There are the usual ridiculous references to things, but basically this is assignment 1 and assignment 2. There's some data sets involved. You can find them in the PDF, or well, no, I haven't put them there. It's in the PDF. What have I done? Yeah, okay. So it could be a Ron Swanson theme. We'll see. That could all get changed. What's that? They may be, yeah. There's no shortage. You do want something that carries you all the way through. I mean, if we look at some I will. If we go back here, so I think Coconut's back here. This was season 7. The theme was Monty Python, which was quite enjoyable. Right. So these are fun. The pantomime horse. This is really for ecologists. This is really enjoyable, right? There's a Jacques Cousteau who fights off an ant or something like that. Very strange. On land. Anyway, so yeah, these are really magnificent. I mean, this thing about aqueducts, wow, unbelievable. All right, anyway, so you want them to be thematically solid, obviously. All right, so those things are there. I am going to work on obviously some weird glitches there. I'm not sure what happened to that, but the way I do this, I'm going to, I know what it is. Symbolic links. Okay, so I'm going to do a better job, I think, of breaking up these things that are recorded here, for better or worse, and just repackaging them a little bit better. And, they're just sort of historical things. That's random. Okay, Pratchett is here. He's always our neural reboot character. The punning, very strong. For those of you unfamiliar, Pratchett is a assistant director of the course. The Towering Inferno, It's just hilarious. Okay, all right. Yeah. Oh my God, it's too easy. Anyway, basically the greatest cat in the world, except for all the other cats. Sorry. Okay. All right. So hopefully you've been able to find assignments. We're going to have office hours really straight after this class today. They'll kind of move around a little bit, but they'll be on Tuesdays and Thursdays back over at Farrell. There's a meeting at 11 for what is being called Story Wrangler, which is our effort to extract stories from social media. So the office hours will firm up as we go along. All right. Okay, let me get the right thing. So I just added these to a sandbox. So let me talk about, yeah, okay, all right, this is good. This is not a bad order to do it. So this is this tiny little landscape, right? It's a 5x5. I thought we could work through this. And you've derived this network, right? And so you can see this. So this, might be a mile resolution or something ridiculous, and we're on the, the contiguous U.S. or whatever, the northern North America. So it's a bit of a funny thing to do, and you can imagine. We talked about this issue of having better and better resolution. It will change these structures, but this is really what you do with a satellite image. And I'll get to how we actually get this next. But you can allow different things. So you could say it's only going to flow to the nearest neighbors, right? So we could do that, the 4 nearest neighbors. Or we could allow this as well, and then there's a square root of 2 that we're going to worry about as well. But let's say this has been derived. So once you've got this network, you want to make a little algorithm that will do the stream ordering and find basin areas and so on. And this will recur in a couple of places. So I've got the example here, and I thought maybe, let's see if I can show some components here. It'll be interesting. So we've got this one. I'll make this bigger. There you go. Okay. Seems dangerous. Why is it doing that? Just do that. All right, okay. It's a bit odd. I'm not sure it can handle the resolution. Okay. So it's exploded again. So this is our, oh, I know what to do. How do I do that? It's, nope, all right. Nope, okay, fine. Make this bigger. So this thing, okay. All right, so let's imagine, so stream ordering would be something like this, right? So you come along here and, let's use blue. It was a good color. So we'd say, this is this thing we talked about the other day, right? So we go to all these source streams and we label them as ones, right? So these will all be ones. So you'd have a little algorithm that has to do that, right? It has to go to a place and say, there are no other incipient things, and I'm going to label all these pieces. So then you have to record all of this, right? So there's a 1 stream coming in from this side, there's a 1 coming in from this corner. So each lattice point that you go to, you're going to have to look at all of its boundaries and see if it's got an incipient stream coming in, and then look at its orders. So you'll have to do this iteratively, right? You'd find all the 1s first, you'd label all of those. Welcome, right? 1s, 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 1s. Yep, and then when 2 1s come together, so this is an unusual, I know what that is. It's turning, sorry. It's a trifurcation, right? So you don't really see this much, but it's going to happen in these this made up thing. So we'd say this is 2 1s hitting each other, so this is going to be a 2. These are 1s hitting a 2, so that will stay as a 2, right? It doesn't change. So we could make this this will be a 2 like this, and so on. Does that make sense? I missed a 1 here. So this will be 1, this is still a 1. 2 1s hit each other, they make a 2, right? So this becomes a 2 here. You can tell me when I'm making mistakes. Hopefully I'm not making mistakes, but that's what happens. Right. Right, we have these new buildings, right? Innovation and discovery. We talked about this, right? There should be, I've made a horrible mistake and it's on fire, or other actual science terms. What was I doing? Or do you want to play table tennis? That would be another one. High quality science. So let's make an orange one. So these are sort of weird things you wouldn't see at large scales, but this will be a 3. Right? And so there's a 2 hitting a 3, but that's just going to get absorbed. This is this idea of absorption. And so the whole thing would be a basin of order 3. Is that sort of all right? Yeah. Did I get this wrong?
Just a quick question. So we talk about how like a 1 hitting a 2 will just be absorbed. But why are we not looking at like, so 1's connecting at the same point to create a 2.
2 1s hitting each other, yeah.
Yes.
I do think this could all be done better, but this has been around for 60, 70 years, and yeah.
Yeah, just like,
yep.
Why would not 2 1s hitting necessarily at the same spot create another 2? Like, it seems like at some point, like if I just have 1s and 1s and 1s and 1s,
yeah.
is it really just going to stay at 2? Because that just doesn't seem plausible. Like I understand that you're absorbed, but
yeah, no, fair enough. It turns out that this stream ordering, it sort of works well enough for you to be able to kind of go up through all the statistics and get to power laws and so on. But it does, and the Tokunaga stuff, which we just got to and I didn't quite finish, shows that there's really nice structure in terms of those side ones, right? So that they can be counted in a nice way. However, I think it could be done much better, yeah. Because once you look at the distributions for things like area, basin area, and stream length, or volume in bodies, whatever it is, they're these kind of very broad distributions, which shows you, and we saw some examples for Mississippi, like an order 8 or an order 9 could be quite small. So that's not really right. It's not really the right thing. So this will work well. It works well. As far as creating a taxonomy, it doesn't connect to the physics as well. That's the thing. So if you wanted to think about, so this is blood networks, of course, river networks, we're thinking of stuff flowing out. If we're thinking about blood networks, we're thinking about flowing in and flowing out as well, right? So we've got the arterial network, and then there'll be this venal network which is attached to it, which has some different properties because it's returning. Then you think, and we'll get to this later on when we get to optimal networks, you have to think about what's the impedance of this thing. And it's very much a kind of a hydraulic story, which is analogous to electrical circuits as well, right? So that you're trying to push this material up here, blood or fluid of any kind, and there's resistance in the tubes and all sorts of things. So, what does this, if you've got a heart here pumping or something just continuously pushing, what does it see this network as? And how would structuring the network in different ways change that impedance? So it's hard to calculate. So what I'm trying to say is it is a bit difficult to calculate the impedance of this thing using stream ordering. There must be a better way to do it. So you should think of that. It'd be really great, actually, to improve upon this. I mean, this has all sorts of goodness that I'll show you, but I think there's another way we could go potentially. Laura. Does everyone have a node in them? Yeah, so you imagine that there's rainfall, so this is a bit odd, obviously, because it's high variability when it comes to rainfall, but we sort of just imagine this over a long period of time, this sort of steady state rainfall. And the way you do it in a simulation is you just have, so this is a lot like Minecraft with irregular shaped heights and so on, right? And I really thought I'll reference Minecraft a little bit, but you imagine your big block of fluid coming down, or a ball, and it hits it and it falls off and flows down through this thing. But that's happening at every point. So you've got this sort of just steady stream of these little blocks coming down, and then they flow down. And so if you think about this in a steady state thing, if you look at this at every time, and it's kind of, right, it hits here and then falls off, hits here and falls off. So if you looked at this, there'd be this sort of this depth of 1. I mean, it's all normalized however you want, but there's sort of depth of 1 here. But this one would have, and we'll get to this now, I guess, there's going to be one falling here, but it's also going to be getting this one every clock cycle. And you could, there's a square root of 2 here you could play with. But, so that's all right, so this is a good place to talk about this. So there's one area there, one area there, one area there, but this one has, so you combine things, right? So you'll say 1 plus 1 plus 1 plus 1 here. So this is actually a 4. So the drainage, and so this makes sense when you look at it, right? This is the basin area for this thing is 4. So your little algorithm, the way to do this is you go to every point and you drop a little block down and you let it fall down the path of steepest descent. And every time you go to a point, you put a bean there. I'm confusing beans and blocks and things. But you imagine a little raindrop, it falls here, and then next time cycle there'll be another raindrop. So let's imagine there's only rain falls in this square. All right, so we just let it do this continuously, and eventually there'll be just this flow of the stream that's coming down, and it's all sourced from that point. But it means it'll start piling up.
Maybe just to clarify the underlying data here, you're looking at elevation within each grid cell?
Yeah. So I kind of got this out of order, and so it's going to be like this. Right. So let me come back to this one, but I was just trying to sketch this out last night. So this is the sort of thing you get from satellite data. It's been cleaned up and so on and put on a big square grid. These are USGS, we'll call them digital elevation models. They're irregular heights, but the squares are sort of made to be uniform. There's curvature of the Earth to worry about a little bit, but basically, these are big matrices. You have a big matrix for the US or whatever you want, and then you imagine water falling down this thing, and that's how you extract the paths. All right, so maybe I should stay here. Did you want to say something more?
Well, just
you do.
there's sort of two related things happening. One is the elevation of the Earth's slope, which is the difference between that and elevation.
Yes, right. So let's see if we can kind of show it. So here's say the data we've got out, and imagine you can't see it on this, but I hashed this. There's a wall here and a wall here, right? So nothing's going to fall off the back. This is some sort of weird Qbert game. Yes, Qbert. Poor sad Qbert, who probably none of you, unless you've seen Wreck-It Ralph. Qbert is homeless in Wreck-It Ralph. It's very sad. They pulled the machine out. Okay. All right. Okay, so we imagine, here's our little raindrop. It's going to bounce off, and we're imagining you can only go in one of the 4 directions here. So it's going to find the steepest descent. Yeah. So this is the lowest one that's adjacent to it. This one is lower, so it's going to go boink, 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 and then fall off in some direction here. And so you do that for every one of these points, and you start to get a network structure. It's going to be more complicated when you allow the 8 directions, and then we've got a square root of 2, so the slope, it's not just the lowest point, because there's you have to divide by a square root of 2 to figure that out. So let's imagine, in fact, that this is lower. This is steeper, I should say, from here to here, but not this one, right? So this is the steepest one, and it bounces off in this direction. And if you do that, I guess that was sort of the idea. You start to build this sort of network that when you look down on you get one of the examples, the sort of the example I just showed you, right? So that this one flows down this way, these ones would flow off in this direction, and they start to form a network structure. You can't get looping in this. Right? I mean, if there's sort of equal heights, you could just do a random choice and fix it. There is one difficult problem, which when you've got a large continent scale thing that you wouldn't get for blood networks, is that there are lakes. And more than just lakes, because you've got some resolution, maybe it's whatever it is, 1,000 meters or something like that. There'll just be patches in here that are just lower than everything else, right? So they're little sinks. So your little algorithm's going along and dropping things down, and it's all falling down, and then it just gets stuck. So to deal with that, you have to go in and find all of those places you get stuck where you didn't reach the border of the data set, and fill it up and just make it a little bit higher than the next lowest one. So I have an old C code that I did for this. And so when you've got a big enough lake, the Great Lakes, right? These are big, sizable things. Is actually, so you'll have a whole patch that everything's the same height, because the resolution of the satellite data is such that it's the same height. So the way to do that is you go to the edge of the thing. So imagine this is our lake. You go to the edge of it, and you find the steepest points off it, and then just add this very thin like gradient going out from it, sort of fanning out from it. So anything that comes down off a mountain here will eventually roll off the edge. So it's just a sort of a way of filling it in to allow this simple algorithm of things falling down the steepest descent to work. So you have to treat it first to make sure that there is an exit point for everything that flows down. I think that code was called kevinlakewaster.c for some reason. Anyway, yeah. So that that's tricky. That's a bit of a trickiness, but I'm not going to make you do that, if that's okay. Is that all right? So this is a good thing to work with. So we'd have these characters here, right? So there's one here, one here. Let's just get to a little bit. This one is going to be a 3, right? So it's because I rotated it. And how do I do this again? I want to. Where's the thing? I've lost my. Oh, here it is. All right, hook. Yep. Good. Okay. Woohoo. All right. So we'll do just a few more. So there's a 1 here, 1 here, and there's this little +1 for this one, but it's getting 4 from here and 1 here. So this turns out to be 7, which you can see, right? It is that area that's being drained. So this will be 11 once we get to this. Right. So you can make a little algorithm do that. This sort of thing. So you want to find the longest stream. So this is different. Now you have to go back up through the network, and we'll have square roots and so on, but the longest stream in this one, maybe, for example, you might go, it looks like it would be, either this way or this way. Well, no, it's actually going to be that way, because of the square root of 2.
Why is that one 11 if there's more coming from the
Oh yeah, there's a whole extra one. Good, thank you. Yeah. Did not see it. Oh gosh, I've got to do all that. I was trying to be lazy. So 1, 1, 1. So we're going to have a 4 here. It's easy sort of to not count no, that's 1, 1, and 1. So 3. 1 plus 1 plus 1 is 3. Mm-hmm. Okay. What do we got? It looks like 15. 3, 3. So 6, 7, 14, 15. Is that right? And so that would be this whole basin. Yeah, 5 by 3, right? If we take this block and put that here, we've got a 3 by 5, so 15. So it will, and so it means that this one will be, you'll get a 25 here, whatever happens, because there are 25 things. Okay, so that's sort of the strategy for figuring some of these pieces out. You can see it requires you to kind of record a lot of things and maybe sometimes go backwards up through the network. Sometimes it's a simple descent thing, but yeah, a little bit tricky. And again, for blood networks, this is going to be a harder thing once we've got it stored in some way. It's going to be in some sort of three-dimensional messy thing. Ideally, you get it down to here are junction points, and they connect off and connect off. Yeah. It's all right. So that was my little extra bit there. Oh, I just destroyed it. Okay. Oof. Okay. Okay. So is it all right? Lara. So you'd start with this one having is that what you're saying? Like this has a length of 1 in here. You just sort of give it a little piece. Yeah. So what you need to be able to do is as you go back up through here, you see how you calculate the mainstream lengths for all these little sub-basins, and as you go up here, you go into the longest direction. So you can make it work in this direction too, I suppose. That's true.
So is it like for each like little dot, or is it sort of extreme like so the first one?
Yeah. So each. So that's that's the important thing about these things, and with us as well, right? Is that there are basins within basins. So every dot has its own basin attached to it. So there's a tiny basin for this one. This one drains this whole area. So each point has its own little basin, which has an area and a longest length and a typical shape. Is that okay? Yeah. So this point here, this is its basin, the whole thing, and that's its longest stream. This one, it's just got this little basin, and so it's an interesting thing to think about. You have to. I'll show you some other kind of interesting pieces about this that I don't think have been figured out. But you have this kind of weird packing problem. It's easy. You have all these basins, but of course they're all overlapping. So you have to be a little careful about that. And this shows you one of the reasons. Right. So this is an extra piece. Okay, Tokunaga, as I said, this is work that came out of Japan and wasn't really known outside of Japan for about 30 years. But it built on Horton's work, which was from the 40s. So these are these order 1 basins on the side that are going into this order 3 stream here. And there are order 1s here going into these order 2s, right? When you think about this, it's a bit of an odd business, right? The order 1s comprise some fraction. If you take all of their areas, it comprises some fraction of the overall landscape. The order 2s as well, right? They comprise some fraction in the order 3s. So, what's that fraction, right? So it turns out that they don't really take up all of space, which is a bit odd. All right, we'll get to that later on. Okay, so here's the idea. We're absorbing streams of order nu into streams of order mu, right? So this could be a 7-order stream, gets a stream of order 5 coming in, and we want to be able to count those things. And so the observation was around these couple of steps. So the first one is based on just a heuristic of, you can assert this essentially, and then sort of test it out, but it's a reasonable thing to think beforehand, is that the difference between the absorbing stream and the stream that's entering it is all that should matter, right? So that once we're away from the order 1 ones and the overall order of the whole thing, there should be enough self-similarity in these systems, which we evidently see that this will be true. So that takes out, it reduces the parameter set, right? So now we've really just got the difference, so that's the difference in here. And if that's true, then there's an extra piece, which is that, like Horton's laws, and there'll be a scaling, right? So that if we set the difference to be 1, right? So if this difference is 1, so we're talking about how many order 6s go into an order 7, or how many order 9s go into an order 10, then this is to the power of 0, right? And so the idea here is there's a typical number of streams of order 2 in this case that go into an order 3, or order 1s that go into an order 2, and so on. And from there, there's this ratio that you scale up with, right? So roughly in this case, well, I'll have an example. But roughly in this little example over here, the ratio is 2. This Tokunaga ratio is 2. You start off with about 2 as well. But usually usually this is around 2. Usually this is around 1 or something. Is that sort of okay? So this is this is an observation. So there's a nice thing to connect, right? So here's our example at a bigger scale. All right. So the first one, and so this is made up, of course, is roughly 2, right? So of course it's made up. So there are 2 side streams of order 2 here. In this one it has 1, 2, 3. It's statistical, of course. 1, 2, and then up here there's only 1 in this case, and then 1 and 2 here, if you can see all these things. but the number of order 1s going into the 3 here is 1, 2, 3, 4, 5, 6, 7, 8, 9. Again, it's probabilistic. Of course, the numbers have to be integers. But this is roughly the idea that if you look at a certain order and then you look at how many side streams of the order below, you'll see roughly 2 on average. And then as you move up through the differences, you'll get a factor of 4. So there should be roughly 8, and in this case there were 9 order 1s going into order 3s. There'll be 16 order 4s going into order 7s, and so on. And so this turns out to be, this is a reasonable thing to suggest. I mean, once you realize it's not a pure hierarchical structure. Again, that's true of us. So this is a really, I think, an important, while the stream ordering thing is not perfect for, say, physics, this does give us something important to understand, that it's not a pure hierarchy, right? That there are these small pieces going into large ones. Which I don't know if you'd suspect that straight away. So this is to show you some data. It's a little bit messy, of course, as you might expect, and it's going to fall apart at the ends. But this is this Tokunaga ratio as a function of mu, which is the absorbing stream. And then each one of these lines is for a particular stream order that's being absorbed, right? So these are order 1s going into order 2s, 3s, 4s, 5s, 6s, 7s, 8s, 9s. Right? So that has to go up. Fair enough? And this is just orders across here. This is a log scale, so it's increasing exponentially, which is what a strict ratio should do. So, it's rolling over a little bit. It's going to fall apart at that largest scale, which is fair enough. It should be a little bit messy, perhaps, at this for order 1s, because that's, again, the other end of the resolution. But it's not too bad, right? So if we look at, say, order 3s, that's here going into order 4s, and then 5, 6, 7, 8. It's not bad scaling here, and then it's going to fall apart. So this is, and then you see some real aberrations at points. So that seems to hold up pretty well. Scaling is very messy, and if you want to look at these things, it's hard. Yeah. So along here, this is just, these ones are the ones where you're looking at the order below, right? These are 1s into 2s, 2s into 3s, 3s into 4s. And they sort of have a bit of a drop. That's fair enough. So that seems like a reasonable, that's one end of this scaling that you expect to maybe be problematic. Right, so there's a bit of it's not great here, and then it's going to fall apart at this other end. And we expect that. Anyway, this shows you it's not bad, and that this is really part of the fabric of these kinds of networks. Again, understanding these things is hard. I have a whole bunch of, so I just fell short of getting there, but of course I've added more stuff, so it's fair enough. Before we go into the second section. So a lot of self-similarity, as we've seen, right? And I've focused on river networks, but we'll get more to the blood network data soon. Where there really are these beautiful theories, too, for why the networks are the way they are. We'll see that they are problematic in interesting ways. Okay, so lots of interrelated scaling laws. I gave you that big list, sort of as the Horton structure. So the stream ordering is a way to get at the architecture. And, if you think about this, maybe you can come up with a better way to do it. But it's been around for a long time, and it's been transported into lots of different areas where branching networks are around. Even people thinking about like seaweed and stuff like that, right? So anything where there's some structure. I really need to do phyllotaxis. Okay. So self-similarity, and this is really the first kind of quantification of fractal structures, as I understand it. Again, in the 1940s, didn't have the word then. It was Mandelbrot, about 20 years later. Right, not a pure hierarchy. Tokunaga really helps. So Horton's laws alone do not give you, so you can't really get Tokunaga's laws. Well, you kind of can, but they don't imply it in a very clear way. And so we'll sort of go through that in the next set of slides. I know it's exciting. So there's a mixed hierarchical structure. These things can be connected. And then surprisingly, there's this sort of thing, right? So this is a bit odd, perhaps, right? It's not obvious straight away. but this is the Horton ratio for stream number. And sitting out here are the pieces floating around from the Tokunaga's law. Right, so that's the ratio, and that's the number for the number of side streams of one order less. So there's some quadratic involved, obviously, right? But it's a little bit odd. And there are some perfect kind of contrived examples that fit together very well. So if you have 2 and 1, for example, I think, yes, then, yeah, which is, you know, not a bad little sort of network to play around with, right? So this would be 5 squared minus 16, so 25 minus 16, we're quite excited about that little Pythagorean triangle, right? So there'll be a plus 3 here. 5 plus 3 divided by 2 gives you a 4. So that's actually sort of not, I mean, that's just a lot. It means that you can make some examples that have integers everywhere, which is sort of nice. But, you know, there are random network ones where there's no analytic solution for these things, even though they're nice random walk type things. We don't know what these are. We know what the power laws are. Okay, all right, so that'll be a good thing to figure out.